All right, so we're going to continue on talking about electric potential, which we introduced last time. And we had talked about this example of a capacitor. If you had a charged particle in the capacitor, and it moved from, say, A to B, some point A to point B, and this is the positively charged side or plate of the capacitor. Here's the negatively charged plate. And so there's an electric force pointing in that direction on a positive charge. That force does work, which would be equal to the force times the distance. So you'd have a force times a delta x. And that force, if this is a proton, for example, has a charge plus E, be plus E times the electric field inside the capacitor, which is pointing this way, times that change in position. And so if we then look at the system of the entire, of both objects, the charged particle and the proton, change in electric potential energy is the opposite of the internal work. So this would be a change in potential energy of negative E, little e, big E, delta x. But for the case of an electron, if you had an electron moving through this same region over the same distance, then the potential energy would actually go up. Okay, it'd be kind of like throwing a ball up in the air, because the force would be in the opposite direction of the displacement. So it'd be tending to slow it down. The kinetic energy would be going down, but potential energy would be going up. So we saw in both of these cases we have this factor of the electric field times a change in position. Okay, and so it's useful then, the only difference is the sign. So it's useful to then divide out the charge dependence and just look at a change in potential energy per unit charge, because if we have it per unit charge, then we can just generalize it to any charge we would have moving in between those same two positions. So we define this thing what we call electric potential, or really the change in electric potential. We'll just be dealing with changes for right now. Which is the symbol delta V being equal to delta U, the potential energy, change in potential energy, divided by the charge. Okay, so we have units of joules per coulomb or volts. 1 volt is 1 joule per coulomb. Okay. Using this and using what we worked out for the potential energy, we found that we could generalize this and say that a relationship between the change in electric potential and the electric field is the negative Ex delta x plus Ey delta y, if we had motion in more than one dimension here, plus Ez times delta z, or more compactly, we can say it's negative of the electric field dot product with delta L. Okay. I should say that this is for the case of a constant or a uniform electric field, but we'll deal just with uniform fields for right now. And the important thing to realize here is we're always looking at, it's a scalar. It's giving us a scalar, like any dot product. It's giving us just a single number. It can be positive or negative, but it's not a vector quantity. We're combining two vector quantities, and those quantities are the field, the electric field, and the path. So delta L is a path vector. So when we're calculating a potential difference, you always want to keep in mind, what is the path? What direction are we moving along a path? And what's the field? What's the electric field along that path? Okay. The path could just be any generic path. It doesn't necessarily have to be a path that a charge is actually moving, because again, we're sort of dividing out the charge dependence and looking at something more general. But there's always a path there that if we had a charge moving along that path, we could then figure out what the change in potential energy would be for that situation. Okay. So this is best the best way to get used to this is to just try some examples.